Hello, class. Today I want you to get out your Chapter 3, Section 1 notes on forces again. Remember, we only went halfway through, so today we're going to go the rest of the way through and talk about gravity, okay? All right, so let's go to where we left off. Here's where we were. We talked about static, kinetic, and rolling friction and ways to reduce friction and ways to increase. Now, let's continue by talking about another force that affects us every single day of our lives, and that is gravity. Okay, typically for gravity, we use a capital F with a subscript little g. So that's gravitational force. F for force, G for gravitational. So gravitational force, okay? Now, gravity is one of the non-contact forces. If you remember, that's a type of force that the objects don't have to touch. The force can be transmitted over an intervening distance. It exists there. It's also an attractive force. Gravity does not repel, it only attracts two masses to each other, okay? And it's one of the four fundamental forces that we talked about on page 1. Now, the first modern scientist to study the effects of gravity and other forces on motion was Sir Isaac Newton. Okay, and of course he was English, and he actually in one night determined what gravity depends on. A friend of his who was an astronomer was having trouble fitting the mathematics of the orbits of the planets to what they should be, but they didn't seem to fit right. So he thought it must be this gravity stuff that Newton had mentioned before that was affecting them. So he wrote a letter to Newton asking if he could send him any of his work on gravity. Well, Newton really didn't have anything written down, so that night he sat down and wrote up an entire document about gravity and its effects, all in one night. The man was a genius. So he came up with what we now call the universal law of gravitation. Universal because it applies everywhere in the universe, between any two masses, anywhere in the universe. In fact, it depends on the product of the two masses and the distance between them squared. Now, if you remember, a product means to multiply. It also depends on the distance between them squared. And he did come up with a formula that he sent his astronomer friend. It looks like this. A proportionality constant to make the two sides equal. And here's the product of the two masses. And then you divide by the distance squared. Now, don't freak out on me. You're not going to have to worry about using this formula, but we're just going to take a look at it to see how things are affected. Okay, so if you have two masses, all right, and they're closer together because you're dividing by the d squared, when the d squared value is small, the force is going to be large, because when you divide a small number into the numerator, the quotient is larger. But if you increase the value of d, make them further apart, and then you increase d here and divide it into the numerator, you're going to get a smaller quotient, a smaller answer. So as d increases, the gravity decreases. And as d decreases, when they get closer together, the gravity increases. Isn't that kind of cool? Okay, so this is showing as d goes down, F sub g goes up. And right here, as d goes up, it gets bigger, F sub g gets smaller. Okay? All right, Now, let's look at the product of the two masses in the top. If one of the masses gets bigger, that makes the product and therefore the gravity bigger. If one of the masses gets smaller, that makes the product and therefore the gravity smaller. So here, as a mass increases, like this one, the gravity increases. But if the mass decreases, the gravity decreases. Okay? In fact, we call this a linear relationship. We call this one a inverse relationship. Okay? Now, it also stands to reason, notice the arrows. Okay? Notice that here, that the arrow that acts on this one from that one is the same size as the one that acts on this one from that one. The two arrows are the same size. That's because the gravity each exerts on the other is exactly the same. Look here, even for the bigger mass, the gravity exerted by the smaller mass on the big mass right here is just the same size as the gravity that the larger mass exerts on the smaller mass here. The two pulls are exactly the same, just opposite directions. Now, how can that be? How can they be exactly the same? Well, I'm going to show you, because you got to understand why it is that way, because so many people think that the bigger the mass, that one pulls harder on that one, and this one pulls smaller on that one. No, it doesn't, and it has to do with this product. Think about it for a moment. Suppose we want to find the gravity that acts on a small mass from a big mass. We would have to say G times the small mass times the big mass pulling it and divide by the distance between them, right? Now let's see, what would it look like if we wanted to find, let me push it up so you can see it. What would it look like if we wanted to find the gravity acting from the small mass on the big mass? So we take the mass of the big mass, the mass of the small one, and divide by d squared. Now look at those. Whether you're talking about the force from the big mass acting on the small mass or the force from the small mass acting on the big mass, the two products are the same. So the entire thing is the same. Each one pulls just as hard on the other, okay? There's no difference just because there's a size difference, all right? Because it depends on the product of both and not just one of them, okay? All right, now, let's talk for a minute about this region that we have around every mass, where if another object comes within that region, it's affected by the gravity. This is called a field. All objects have a region around them of gravity, and we call that a field, okay? And fields, gravitational fields, can extend a long way. Think about the sun. Its gravitational field extends way, way out beyond even Pluto, the smallest little planet in our solar system. It extends so far out that even the Oort cloud in our solar system, which is way, way out there, it contains the comets. Even the comets are affected by the sun's gravity, and that's why they return again and again after many years. Okay, so gravity is a very long-range force. Now, something else I'd like to talk to you about for a moment is how gravity affects objects on planets. Now, when we talk about the gravity acting on an object from a planet, say your desk at home or your laptop here on Earth, it's affected by the Earth's gravity. And we have a special name for the gravity a planet exerts on an object, and we call it weight. Weight is actually a synonym for gravity. And if you're not sure you remember, synonym just means a word that means the same thing. So weight means the same thing as gravity. They're two words for the same thing. It's just that when we talk about weight, we specifically are talking about the gravity acting on an object from a planet, like your laptop, your bed, the chair, a sofa, yourself. All of these things are acted on by the gravity from planet Earth. So we call it your weight. Now, here's what you need to understand. And this is a real problem in science because people don't want to think about it. They don't, and they misinterpret. They have a misconception about this. But, and this is so important, mass and weight are not the same thing. Weight is gravity, okay? So weight is gravity pulling on you. All right? Mass is the matter you contain. Okay? So when we talk about mass, we're talking about the measure of matter, the atoms and molecules. When we talk about weight, we're talking about a force, a push or a pull. Matter is not a push or a pull, it's stuff, okay? So you need to know the difference. Mass is a measure of matter. Weight is the force of gravity pulling on you from a planet. Now, there is a shortcut way to determine gravity or weight. And yes, if you wish, you could use a W to represent weight. Most scientists, they will use a W when talking about weight, but I used an F sub G to help you remember that weight is gravity. And there is a shortcut way to find the gravity acting on you from a planet. You don't have to use this big formula to find the gravity between you and the Earth, okay? All you need to know is the mass of the object, whatever it is, and the acceleration the object would have in free fall, okay? We use a little g. In fact, I'm not going to do that. I'm not going to use that little g because it confuses too many people. Where's my whiteout? Okay, we're not going to use that little g, so we're going to modify it. Okay, we're going to say the mass of the object times the acceleration due to gravity. There we go. So the force of gravity equals the mass of the object in question times the acceleration due to gravity. Now, what do I mean by the acceleration due to gravity? I'm talking about the acceleration an object would have if the only force acting on it were gravity. Now, it doesn't have to be in reality, but if the only force were acting on the object, then the mass of the object times its acceleration would be its weight or gravity on Earth. Now, every planet has its own acceleration due to gravity. It has to do with the mass of the planet. On Earth, the acceleration due to gravity has the value of 9.8 meters per second squared at the surface. Okay, in fact, you have to go away from the surface of the planet in order for the acceleration due to gravity to get smaller. Because remember, the further away you are, the further away two objects are from each other, the weaker the gravity is. The weaker the gravity is, the smaller the acceleration. So at the surface, and for about a mile or so up from the surface, the acceleration due to gravity is about 9.8, okay? And then if you get several miles up, it changes to about, where is it? Here we go, the next one, to about 7.4, okay? So right over here, this is the surface value. But if you go up like satellite height, it's about 7.4. If you go even higher than that, further away, it changes to about 9.4. Further away than that, about 2.5. And look, way out here, way out here, about 0.98. So it does decrease the further you get away. And each planet has its own acceleration due to gravity when gravity is the only force acting on the object. In fact, that would make the object fall. In fact, we would call this the free fall acceleration. You remember I talked a little bit about free fall in chapter 2, just touched on it barely. Free fall is what an object does when the only force acting on it is the gravity from the planet. And the acceleration you have in free fall is this one on Earth. On the moon, the value is 1.63. And on Mars, the value is about, I want to say 3.4 if I remember correctly. And I think on Jupiter, a huge planet, I think it's like 25 something. All right, so anyway, the shortcut way of finding the weight on a planet, you have to know the acceleration in free fall on that planet, and you have to know the mass of the object in question. And then real quickly, you can just say mass times acceleration, and you've got the weight of the object on that planet. Okay? All right. So now, let's take a look at free fall for a minute. Let's actually define it. Let me make sure y'all can see this. Okay. So free fall. This is what happens when an object has only the force of gravity acting on it. We say the object's in free fall. For example, when a skydiver goes up in the plane and jumps out, before he opens the parachute, he's considered to be in free fall. So his acceleration would be about 9.8 meters per second. In fact, in free fall, how would you feel? You would feel actually weightless. Now, does that mean you are weightless, that you have no weight? Wrong. When you're in free fall, you feel weightless because you don't feel the Earth's gravity acting on you at all, ever. You never feel it. So why do you feel weightless when you're in free fall? Well, it's because there's nothing pushing up on you to give you a sense of heaviness. When you're sitting in your chair, you feel your usual heaviness because of the chair pushing up on you, keeping you from falling. If you were in free fall, there would be nothing pushing up on you, so you would feel like you're weightless. You're not really, but that's only because you can't feel Earth's pull. Okay? Now, let's do something kind of fun. I think you're going to like this. Believe it or not, guys, when you go into the bathroom and you step on the bathroom scale, or you go to the doctor's office and step on their scale, you are not weighing yourself. That is a big misnomer. That means misnamed. You are not weighing yourself. You're massing yourself. When you step on the bathroom scale, it tells you your pound mass, how many pounds of matter you're made up of. It doesn't tell you your weight, because your weight is a force and it's measured in newtons, not pounds. So I want to show you how you can calculate your weight on Earth. The first thing we need to do is realize that when we're working with newtons of force, our mass, our pound mass, needs to be in kilograms. And most people don't usually know how many kilograms of mass they have. Now, if you live over in Europe, yeah, you probably do, because their bathroom scales are measured in kilograms. Ours are not, though, because we're still stuck back in the old English system. Isn't that awful? Everybody else in the world but us. Okay, so here's what you do. you're going to take your number of pounds. Get your calculator and try this. It's kind of cool. Take your number of pounds, and you're going to divide it by 2.2 because it takes 2.2 pounds to make up an entire kilogram of mass. So your number of pounds, divide by 2.2, and that's going to give you your mass in kilograms. Okay? Now, let's say that you weighed 110 pounds. So we're going to divide that by 2.2, and when we do that, we get 50 kilograms. You're going to kind of like that because it looks like you've lost weight. No, you haven't. Kilograms is always going to be the smaller number than the pounds. So there's your mass in kilograms. Now, to get your gravity or weight on Earth, we're going to take your mass in kilograms. So whatever you got when you took your pounds and divided by 2.2, put it right there. And then we're going to multiply by the acceleration on Earth. Okay? And when you say 50, well, when I say 50 times 9.8, I get 490 newtons. Okay? Now you try it with yours. You take your pounds, divide by 2.2. That answers your kilograms. Multiply it by 9.8. What you get is your actual weight on Earth. And you're probably going to get something between 400 and maybe 900 newtons. Okay, that's usually about average for most teenagers, somewhere between 400 and 900. So check it out. It's kind of cool. So you can tell your parents, well, you have a certain weight and it's not what it's on the bathroom scale, okay? Now, this is going to be even more fun. What if we want to find our weight on the moon? Now remember, the moon is a smaller planet than Earth. In fact, it's considered a planetlet. So it doesn't pull as hard as Earth does because it is smaller. Less mass, less pull, remember? So what we're going to do is we're going to do the same thing on the moon that we did on the Earth. Take your mass. We're going to find our gravity on the moon. Okay? That's F sub G, moon. All right? And we're going to take our mass. And this one's 50. You use whatever you got for your mass. Multiply now, not by 9.8, because that's only on Earth. On the moon, the acceleration is 1.63 meters per second squared. So if you multiply your mass by that, then you're going to get, well, whatever you get on your calculator for yours. For this one, it's 81.5 newtons. Look at the difference. On the Earth, 490. But if I go to the moon, 81.5 newtons. Wow, you lost a lot of weight going to the moon, didn't you? Talk about an instant diet. Well, actually, the weight is the only thing you lost. You didn't really lose any mass. When you come back to the Earth, you'll have the same weight again, right? Your mass stays the same everywhere. Only the gravity, the weight changes from one planet to another because the acceleration is different, but the mass stays the same. Okay? Now, scientists can actually determine the acceleration due to gravity on any planet. I'm going to show you how they do it. It's kind of cool, guys. If you're wondering how they know that on the moon it's 1.63 or on Mars it's 3.4 or things like that, how do they know? Well, here's how. Remember, we have two ways of finding gravity. We can use Newton's universal law. Mass of the object, mass of the planet, divided by the distance between them squared. We can also use the shortcut. We can say the mass of the object times the acceleration due to gravity on that planet, right? Okay, well, if both of these are the gravity of that object on the same planet, we can set these two expressions equal to each other. So watch this. if I say the mass of the object times its acceleration due to gravity on the planet equals big G times the mass of the object times the mass of the planet over d squared. Watch this, watch this, watch this. Now, mass of the object here, mass of the object here. If we divide both sides by the mass of the object, it completely cancels out of the formula. And look what we're left with. We're left with the acceleration due to gravity on a planet depends on the mass of the planet divided by the distance from it squared. So you know what this tells us? The acceleration due to gravity on Earth of falling objects depends on the mass of the Earth and how far the object is from it. It does not depend on the mass of the object. This is why a bowling ball and a tennis ball would hit the ground at the same time if you drop them from the same height at the same time. The acceleration on any planet does not depend on the mass of the falling object. It depends on the mass of the planet. So look here. Let's say that I had a bowling ball and a tennis ball, and I dropped them from the same height at the same time. Which one would reach the ground first? Neither. They'd both hit the ground at the same time. Okay? They both hit the ground at the same time because they have the same acceleration due to gravity. Because their masses, the mass of the bowling ball, the mass of the tennis ball, canceled out. Okay? So it only depends on the mass of Earth and how far they are from it. So they will hit at same time. Now, and this is the ground right here. So guys, think about it a minute. If they ask you, all right, if I drop two objects and one is heavier and one is lighter, when do they hit the ground at the same time? When do they hit the ground if you drop them from the same height at the same time? They hit the ground at the same time. They both start from rest. They both accelerate the same distance. And they have the same acceleration, so it takes the same time. Okay. In fact, it was Galileo who first figured that out. He took some objects up to the top of the Leaning Tower of Pisa in Pisa, Italy, and he showed that one big mass, one small mass, if he dropped them at the same time, they hit at the foot of the tower at the same time. He showed that. Pretty cool stuff, huh? Okay, we're going to stop right there for now. And tomorrow, you're going to do some things, a discussion with gravity, and then we're going to look at some problems. We might even do a little lab if I can get one together. So you guys have a good week, and I'll see you later. Bye-bye.